we are looking at a scenario wherein we have an object moving in circular path. The movement is so that the speed is constant, but it is said to be accelerated motion, right? This is an example of accelerated motion. How can this be an accelerated motion? Well, when it comes to acceleration, which is a vector quantity, you have your magnitude part and your direction part, right? So acceleration has to do with, actually, I should go in this manner. Acceleration has to go with change in velocity. Velocity in turn has two aspects to take a note of: magnitude and direction. Now, magnitude is fixed, but the direction is changing, and so it is said to be accelerated. Now, there has to be a cause for an object to move in circular manner. This you will understand in your fourth chapter, but now, as of now, it's common sense that if I am changing something, if the object is said to be accelerated, as per your 9th grade knowledge, if you guys remember, there has to be a force. As there is acceleration, there has to be a force, and it needs to have direction as well, right? And it needs to have direction. Now the question is, what is this direction? Or indirectly, we are looking at the direction of this acceleration. This acceleration is making what? This acceleration is making the object go round and round. So this is making object go round and round, but with constant speed. Do you guys agree? So the one which makes an object go round and round with constant speed has a special name, and that name is centripetal acceleration. Okay guys, the only job that the centripetal acceleration is to make the object go round and round. Keep it in one path. The speed increasing and decreasing is not of its concern. All it has to do is just see to that the object points, or no, I should not tell you guys that. The object goes in a circular manner. That's it. And this will be directed towards the center and all of that. That will be proving it now. So all of this, text and everything, whatever conversation we had from the last 2 minutes, is to introduce you guys to the topic of centripetal acceleration, and to tell you guys that it plays only one role, and that role is to make the object go round and round, and it does not play the role of making the object go faster or slower in the circular path. For that, we have something called as tangential acceleration, that we'll be talking about it in a second. So where is it? Yeah, tangential acceleration. We're talking about that over here. For now, we're just talking about something called a centripetal acceleration. It is actually, if you literally break it up, it is known as central seeking acceleration, because it makes the object go round and round. When an object moves in a circular path, something has to constantly push or pull it towards the center to keep it going off straight in a straight line. This inward pull or acceleration is what keeps the circular motion going. Okay. The centripetal acceleration is the linear acceleration of an object moving in a circular path. It is always directed towards the center of the circle and responsible for continuously changing the direction of object's velocity, thereby maintaining the circular trajectory. Right? Whatever I just told, it's written over here. Now let's look at the math. Okay, now we're looking at the math. So if you guys want to write something from here, please do. I'm erasing this now. So we are looking at an expression for centripetal acceleration. So for that, I'm considering the same object. It's moving at a constant velocity, but because the change in direction is happening, so we have two different velocities over here. But in terms of length, they are the same. So this is v1 and v2. The same two vectors, I've placed it over here. That's for a reason that I'll be talking in some time. So it's a bit congested. What we're looking at is v1 and v2. Say this is moving in a circular path of radius r, right? And that's it. For now, let's make use of this. Okay, so we'll start off with, since we are talking about acceleration, it's a good idea to start off with the velocity. Change in velocity, right? We need to have a look at change in velocity. So v1 to v2. So this is from and this is to. So I have copied the vectors. I have moved it. Again, if you guys understand, if you remember from vector chapter, you can move these vectors, right? In this manner, we can move it. So I moved it. So let me call this with a name. Let me call this as PQR. Now let's applying triangle law of vector addition to triangle PQR. So as per the triangle of vector addition, if this is PQ and you have this line, if I add this two up, I'll get PR because this is your final position, right? This is the initial part. You added this and you got this. You guys agree? That's what your triangle law helps you with. That is to tell that these two vectors adds up to this vector. Now, I'll rearrange this. So I'll write PR is equal to, QR is equal to PR minus PQ. But PR is already V2 and PQ is already V1. So basically this is representing what? Change in velocity. So QR is representing change in velocity. Okay guys, right? Now we can get one more expression for your velocity. That is from triangle, say OAB. And I'm telling triangle, so I need to join this. And the change in angle, I'm calling it as delta theta. Because AOAV is 90 degree. This is 90 degree and this is also 90 degree. These two are 90 degree. Okay, so let me increase the brightness. This and this, can you see that? Or let me use white. Can you guys agree that these two angles are 90 degree? Because these two angles are 90 degree and AO and OB are at angle of 90, delta theta. This also will be delta theta. Okay, yes. So if you do the bit of math, you'll understand that this two is delta theta. So we are making use of this delta theta now. So we have to, discuss that. So we did. And now let's move on to this one thing. See, as delta t tends towards some small value, not 0 though, delta theta will also tend towards small value. Agree? Then the actual path AB will be equal to the line segment AB. So people who didn't understand that, let me explain this way. The actual path is AB is this, right? Something like this. It's this. That's our AB. This is the actual path. Now what I'm trying to tell is, since this angle is kind of small, if I consider a small value, this arc length and this straight line length will be the same. This straight line length, this is a straight line, that is AB. This is the line segment. AB is arc. So this is AB as an arc. This is AB as a line segment. So what I'm trying to tell is, dono will be same, both will be same, provided we have delta t tending to a small value, delta theta will tend to a small value. So for small time interval, we can consider AB, arc AB to be equal to length AB, the line segment AB. Okay, yes. Now let's consider this two triangle. It's a triangle OAB and triangle PQR. It'll be too much back and forth. So what will I do is, I can take a copy of it over here. We'll erase this when we don't need it. Okay, now let's consider this two triangle. These two basically. So are they similar? Let's have a look. We have QPR, which is equal to angle OAB, which is equal to delta theta. Okay. Then we have, say, AB, not AB, sorry, OA by OB, which is radius. So they are equal to 1. And also we have in this triangle PQ by PR are also equal to 1. These are equal because of them being both are radii of same circle. Both are radii of same circle, while this is equal because the motion is uniform motion. So the velocity, magnitude of velocity are same. And so this two will give us 1 and this two same radius. So this also will give us 1. If I rearrange them, PQ by say OA is equal to OB by PR. So if I use all of them, this is 1 and this is 2. So from 1 and 2, what can we tell? From 1 and 2, what can we tell? We have one angle, one side, another side, one side and the corresponding sides are equal. Therefore, triangle OAB has to be similar to triangle PQR. OAB, PQR. Agree? So that will be that. So what can you do with this? We can write, oh, actually I needed that. So from this we can write OA by PQ is equal to, OA by PQ is equal to QR. Oh, sorry, not QR. OA and PQ. And we have AB is equal to QR. Agree? I hope you guys remember similarity. This is by corresponding part of similar CPST, corresponding part of similar triangle. Now, OA is your radius, while QR is your one of the velocity in terms of magnitude. AB is your what? AB. Oh yeah, I forgot AB. See, AB is what? AB is nothing but your change in position. Agree? Change in position. Displacement basically. Okay. So, AB has to be delta S. That's the length that the object has got displaced. As simple as that. And QR is your delta V. So with this, we can continue now. Okay, there I can. It is. Right, guys. This is from diagram. A bit of rearrangement. We have delta V is equal to V by R delta S. Now I'm going to dividing delta T both sides. We have delta V by delta T is equal to V by R delta S by delta T. Okay, till now it's quite simple, right? And we are pretty much done also. That's it. All I have to do is applying limits on both the sides, sorry. So applying limit or taking limit delta T tends to 0 on both sides. So this will give us what? Well, this will give us limit delta T tending to 0 delta V by delta T is equal to V by R, both are constant. Limit delta T tending to 0 delta S by delta T. Because these two are constant, I can take it out. If you don't understand this again, you need to do limits. This is nothing but the very definition of acceleration, V by R. And this is nothing but your, any guesses? Yeah, let's go back to the diagram. Delta this AB by this displacement by time. What should it be equal to? Yes, this velocity itself, V1, V2 in terms of magnitude. Let me actually call that. If I write it, I think that'll help. All these are equal in magnitude. I'm calling that as V throughout. So they are equal to V. Okay. So this entire thing is equal to V. And this is constant, by the way. And this is nothing but your centripetal. This color. Yeah. This is nothing but your centripetal acceleration. Okay. So if you want to substitute V as omega R, this too we have seen. Guys, again, this is a central seeking acceleration. So we will end up with omega square R. So these two are your expressions for, a force that is pulling the object towards the center. And so it is going, because it has certain speed, it is going in circular path. Okay. So that's that. Now, direction aspect, last part. For that, I need to make use of this, guys. The length has to be, exact. So I'm copying that over there. I should have had more space actually. But anyways, still workable. Okay, so this is your vector and this is your, those are your radius. This is your resulting change in velocity. So this has to be your, direction of acceleration. This we have learned from your first topic also. See, whatever the direction of force is there, that will be the direction in which the velocity will change. And whatever the direction of force is, that will be the direction of the acceleration. So since I am looking at direction of velocity to be down and towards the center, the direction of acceleration is also towards the center. See, basically what I have done is I have considered this length, I'm considering the center, aligning the center of aligning the center to this line. So basically if I copy this, technically if I've done the right diagram, it should be pointing towards the center. Can you see that? I mean, I didn't do any kind of manipulation. Can you see that it's pointing towards the center? That's the funda. Okay. So yeah, so that's that. So direction of acceleration is towards the center. So basically, instead of all of this, right, all of this complicated thing, when we have delta t tending towards 0, right? So even this I can ignore. I can just talk about this particle moving this way. So the acceleration will be pointed towards this. So basically they have an angle of 90 degree. If this is a velocity at a particular point of time, your AC will be pointing this way. If I happen to consider anywhere else, right, let's do that. So let me choose it somewhere over here, maybe here. Okay, so let's consider that. For this case, right, your radius would be something like this. I think this will be the center. That will be the radius. That will be the tangent, and the angle between them is 90 degree. And that is the direction of your, yeah, that will be the direction of your acceleration. Okay, so it's always pointing towards the center. So one last note. So please note that in uniform motion, an object speed is constant. So the only acceleration present is centripetal acceleration. This acceleration just changes the object's direction. When the object speeds up, that is the rate of change of angle is changing, it's not constant, or it's actually, yeah, it's not constant. So object speed is also changing as it moves in a circular path. We call it as non-uniform motion, non-uniform circular motion. In this case, you will see second component of acceleration, that is your tangential acceleration, which is responsible for the changing the object speed. So this is a bit of extra information for this slide, for this video. So now you guys can copy this. Then you guys need to copy from here.